We are on the internet pretty much every second of every day. But have you ever really stopped to think about the invisible high-speed dance that makes it all work? Well, today, we're going to pull back the curtain on the incredible journey your data takes every single time you click, post, or send.
I mean, seriously, think about that for a second. You hit send on a message in New York, and it just appears on a screen in Tokyo almost instantly. How is that even possible? It feels like straight-up magic. But what we're going to see is that it's something way more impressive. A brilliantly designed system.
So, the secret sauce to the internet's insane speed and reliability isn't some single genius invention. Nope, it's actually a brilliant idea about organization. The whole unbelievably complicated process of zapping information across the planet has been broken down into a series of simple, manageable steps, or layers. And this, right here, is the master key to understanding everything. A layered architecture looks at a giant problem, like, global communication, and basically says, okay, let's not try to solve this all at once. Instead, it gives each layer one specific job to do. A layer only has to worry about talking to the one right above it and the one right below it. This makes the whole system incredibly flexible and way easier to manage.
The absolute best way to picture this is to think of a global postal service. You start at the top, right? That's the application layer, where you write your email. Then the transport layer steps in and decides how you're going to send it. Do you need tracking and delivery confirmation like certified mail, or is a simple postcard good enough? Next, the network layer slaps on the full destination address, and finally, the link layer handles that very first step of the journey, just getting it to the local mailbox for pickup. See? Each layer has just one job. It's brilliant.
Now here's where the story gets really interesting. This whole system wasn't just created from one universally agreed upon plan. Oh no. Back in the early days, there was a huge debate. There were two different models, basically two competing philosophies, fighting it out to become the standard for how all computers would talk to each other.
Okay, so in one corner you had the OSI model. It was beautiful, really academic, and super detailed with 7 distinct layers. It was, for all intents and purposes, the perfect system, on paper. And in the other corner you had the TCP/IP model. It was way simpler, more practical, with just 4 layers. It wasn't as theoretically perfect, but it was tough, it was robust, and it just worked. And as we all know, in the world of technology, the thing that works in the real world almost always wins.
So, let's take a look at how they actually stack up against each other. You can see right away that the TCP/IP model, our reality, is just a lot simpler. It basically took the top 3 layers of that fancy OSI model, application, presentation, and session, and squished them into a single application layer. It did the same thing at the bottom, too. This no-nonsense practical approach is exactly why the protocols we hear about all the time, like HTTP for websites, TCP for reliable data, and IP for addresses, all fit so perfectly into this 4-layer model. All right, this is the fun part. Let's actually follow a single piece of your data, what we call a packet, as it goes on its amazing trip from your computer out across the wild internet all the way to its final destination. And we'll use our trusty TCP/IP model as the map.
So our journey starts at the very top, in the application layer. That's your web browser, your email, whatever you're using. The moment you hit send, your data drops down to the transport layer. Now the first thing that happens here is your data gets chopped up into smaller, numbered pieces called segments. But before they can go anywhere, a really important decision has to be made.
And that decision is, are we using TCP or UDP? Think of TCP like making a phone call. You dial, the other person picks up, you both say hello, and only then do you start the real conversation. It's super reliable, you know they're listening, and you get confirmation for everything. This is perfect for stuff like emails or downloading files where you need every single piece. Now, UDP is like sending a postcard. You just write it and you drop it in the mail. You have no idea if it'll get there or when or in what condition. It's fast, but it's not reliable. So it's great for things like video streaming or online gaming where speed is everything and losing a tiny bit of data here and there is no big deal.
Okay, so the choice is made. Our little segment now drops down another level to the network layer. Here, it gets wrapped up in something called an IP packet. And this is where the all-important destination IP address gets added. This is the full global mailing address that tells the entire internet exactly where this one packet needs to go.
And finally, we hit the link layer. Here, our IP packet gets put inside another wrapper, this one called a frame. This frame has the local address. Not the final global destination, but the physical address of the very next device it needs to talk to, like your home Wi-Fi router. It's basically the instruction for just the immediate next step on its long journey. Okay, so now our data is all wrapped up and ready to go. And this is where the absolute genius of the Internet's design really kicks in: packet switching. You see, all those little packets from your one email don't have to travel together like a convoy. Nope. Each one can find its own fastest route through the Internet, dodging traffic jams and network problems. This is what makes the Internet so incredibly resilient. If one road is blocked, the packets just find another way to get there.
So once all those packets finally arrive at their destination, the whole process just happens in reverse. It's like unwrapping a gift. The receiving computer tears off the frame to read the packet, then tears off the packet to get to the segment inside. And then, thanks to TCP keeping track of all the numbers, it puts all the segments back together in the right order to perfectly recreate your original message.
Okay, I know that was a lot of technical stuff, but why should you even care? Why go through all this hassle of layering and wrapping and unwrapping? What does this seemingly complicated system actually do for us?
Well, this is the big payoff. This whole architecture is genius for a few huge reasons. First, scalability. You can invent a brand new technology like Wi-Fi, and it only has to worry about how to work at its own layer without breaking anything else. Second, interoperability. A phone made by one company can easily talk to a server made by a totally different company because they've all agreed to play by the same set of rules. And finally, it makes fixing things so much simpler. If something breaks, you can figure out which layer the problem is in and fix it without having to tear apart the whole system. It's what's allowed the Internet to just keep growing and changing for decades.
Let's be honest, the TCP/IP model is one of the most successful feats of engineering in human history. But it was designed for a much simpler time, an era of just sending basic text. Today, it's powering a world of virtual reality, artificial intelligence, and trillions of connected devices that its creators could have never even dreamed of. And that leaves us with a pretty fascinating question. Is this foundation, this layered system, strong enough to hold up the future we're building on top of it? Or will the next great leap online mean we have to tear it all down and design a whole new set of rules from scratch?